Hi, this is Fig Tuition, and this is a quick review on the vectors part 2. Last time for vectors part 1, we talked about definitions of vectors along with how we do vector addition, some direction ratio theorem. We talked about dot product and cross product. Okay, now we are going to move on to objects in vectors. So there are three main things you need to know in vectors: points, lines, and planes. And apart from just knowing them, we also need to know about how they relate to each other, such as finding a distance of a point from a line, a distance from a point from a plane, etc. Okay? So we see that a point is simply just a point. Well, so it's a vector usually represented in like OP, where O is the origin and P is the point that of interest. So this point tells us the position is basically a position vector. This point can be represented as a vector. There's a 2D point where x and y are the magnitude of the components of the vector. It's also possible to write the vector as a combination of non-parallel vectors. Suppose there are non-parallel vectors u and v. OP can be written as something like this. So for example, we have a u that is in this direction and a v that is in this direction. We can write it as maybe 1, 2, 3 u's then plus 2 v's, something like that. As long as they are non-parallel. The reason for the non-parallel condition is that if it is parallel, then you can only access points that are in that direction. But because they are non-parallel, you can pretty much access the entire 2-dimension space. So in the case of a 3-dimension space, then we need a combination of 3 non-parallel vectors. And it will be written as maybe lambda, mu, and maybe gamma, and a third vector, w maybe. Okay? If it's a 3D. In essence, this actually tells us that to properly define a point in a 3D space, you need 3 unit vectors, you need 3 non-parallel vectors. In a 2D space, you need 2. In a 4D space, which you won't really touch about in A-level, you will naturally need 4. Okay? This is just an intuition you can grow about vectors. Moving on to the second object is a line. Practically, we require 2 pieces of information. Either we need the direction of the line and the coordinate of one of the points. So it's like we know that from the origin, we can find a point. And from this point, we can say that, along this direction is the line. And that gives us a line, right? Or we can just know 2 points. And with these 2 points, we can tell us, hey, along this direction is the line that we want. So either of these 2 cases will be able to define a line for us. There are 3 forms of a vector. There are 3 forms to represent a line in vector space. It's called the vector space, it's called the vector form, parametric form, and Cartesian form. So the vector form is written as this. L tells us all the possible points on this line. M, in this case, tells us the direction of the line. And A tells us a point on the line. Lambda is just a number. It's just any number. So again, this is like telling us, hey, we have starting from O, we have A, vector A, then giving us this point, maybe P. And we have a direction M. And we can multiply this direction M with any number. So that will give us all the points along this line. So as such, this forms a line. The parametric form is basically a broken down form of the vector form, because we know that the vector form is L equals to lambda M plus A. We can write this as a x, y of all the possible points equals to lambda mx, my plus a, ax, ay. So actually we are just writing the vector form as its parametric forms, as its individual component. So when this happens, its parametric form and vector form are basically interchangeable. and very useful. Next, we have the Cartesian form. Cartesian form is, you can think of it as writing the parametric form again in a different way, except now we make lambda the subject. So we see that between these two equations of the parametric form, lambda is being shared. And lambda, since it's shared, they are equal to each other, and they can be written like this, equal. Right? You can check this quite easily by just manipulating. Make lambda the subject, and you can see that how the Cartesian form work. Okay? If one or more of the direction vector is 0, okay, that means if one or more, let's say one of this is 0, then it can be written as its known coordinate. So because if the direction vector is 0, that means it doesn't change in that direction. So we just drop that term from the Cartesian. So we just ignore this, and we just write it like this. Whereas the y will just be equals to a constant. Okay? Yeah, and if you pay close attention, which is what I've explained, you will notice that all three forms are essentially rearrangements of each other. This is very important because each form might be more useful in a different scenario, and it's useful to be able to convert between each of these forms. Do some practice. Look at some of your questions that maybe you have already done, or example, tutorial questions. Try and convert lines from one form to another, and see if you're able to do that. Okay, so if a line is parallel to a plane in a 3D space, like a axis plane, okay, this is axis plane, this is not any general plane. So for example, the XY plane, or the YZ plane, or the XZ plane, there are only 3 possible axis planes. So when it's parallel to a plane, the third component of this direction will be 0. Okay? So for example, if it's parallel to XY plane, then the Z component will be 0. If it's parallel to the YZ plane, then the X component will be 0. And if it's parallel to the XZ plane, the Y component will be 0. Okay? It's basically like the line only exists on those 2 planes, so the last component just doesn't change, right? Okay. Next, relation of lines with other lines can come in 4 ways. One is that they can be parallel to each other and intersecting. If they're parallel and intersecting on each other, then they're basically the same line, right? Because intersecting means they have the same points, and if they're parallel, that means they point in the same direction. So eventually they are just basically two of the same lines. Next is intersecting but not parallel. Then we can tell that direction vector, in case, not sure if I mentioned it, but direction vector is basically this M. Okay, this M is the direction vector. So in the case of not parallel, then direction vector of course won't be pointing in the same direction. And you can verify that unique values of lambda 1 and lambda 2 exist such that lambda 1 m1 plus a1 equals to lambda 2 m2 plus a2. This is basically saying that your points, there will be points where they are the same. When they are the same, what do you mean? What does it mean when a point lies on when the same point lies on the 2 lines? That means that's the point of intersection. Okay? So yes, you can verify this. Just plug in the values. Each of them are called basically lambda. Then you have mx, my, m1x, m1y plus a1x, a1y equals to lambda. Then you plug in the values. Okay? And you can show that there will be a unique point that fits this. Okay, next, if they're parallel and they do not intersect, then the direction vectors are parallel. So that means the 2 m's are a scalar multiple of each other. So the 2 m's do not necessarily have to be the same for them to be parallel. They can also be scalar multiple. We talked about this for the definitions of vector earlier. Okay, so when they are not intersecting, that means none of their points will actually lie on each other because it's 2 parallel lines. They are not the same line. Okay, and finally we have non-parallel and not intersecting. Here then we can see that the direction vectors are not parallel and no points lie on each other. No point lies on each other. So this thing cannot be solved. this equation cannot be solved. In case you are a bit confused, I think I should explain this a little bit better, because when we have a line, we will know the direction vector, we will know the point, we can define the line properly. So the unknown in this case, right, is really just a matter of lambda 1 and lambda 2. So there are two unknowns here. And we notice that when we break them down into its components, we can form one equation using all the x component, we can form one equation using all the y component, and then we can basically find that this is basically a simultaneous equation, right? So it's essentially a simultaneous equation where you can solve it and find the answer. If it's 3D, it's the same thing. Just equate this, solve the simultaneous equation, find the two lambdas. Okay? So, yeah, in fact, it's written here. Yeah. Okay. And that concludes most of the lines interaction with each other. Next, we have the planes. So for planes, we require at least two pieces of information. To define a plane, we need a point on the plane and the normal to the plane. So a normal to a plane is like this, and we need to know a point on the plane. Any point will do. And then that would tell us, okay, hey, with that, we know that any point that is we know that from this point, from this normal, we can see that there is perpendicular points to this normal. There are perpendicular points to this normal, and all these perpendicular points lie on this plane. Another way to do it is to find the perpendicular distance from the origin. So let's say there's a point here, OP, but then if we know the perpendicular distance, we can also just say, hey, we know that the plane is this distance away, and we know that it's pointing in a certain given direction. Therefore, all the points that has a perpendicular distance of, let's say, d away, pointing in that direction, can be found to be on the plane. Okay. Next is three given points on the plane. Three given points on the plane will naturally be able to form a surface unless they are collinear. So three given points, they must not be collinear. And this will be able to define a plane, because yeah, three points you can form. This will uniquely give you a plane. And finally, two non-parallel intersecting lines. So if you have non-parallel intersecting lines, we know that there's a point that they meet. We can form a plane using these 2 points. It's a bit hard to visualize, I believe, for some of these conditions, but don't worry, just try to visualize it. It's not super important to be able to visualize all of them. What's important, however, is to be able to understand the different forms of plane that you can represent a plane, which is this section here. Okay, the above is good if you can understand. It will help you a lot with the intuition. But what's most important is to be able to understand all these different forms to represent the plane. So a scalar product form is when you have a point and a normal vector. We can express all the possible plane as R, and we can see that we'll use back this illustration. We'll see that R, let's say this is an arbitrary point R, and this is A. We can see that RA is a vector that lies on the plane. And if it's a vector that lies on the plane, it will be perpendicular to the normal. The normal, it just means perpendicular, okay? So yeah, it may not, yeah, again, let's just redefine this. A normal is just a vector that is perpendicular to a plane, in case it's not known yet. So we know that RA is, or AR in this case, is on a plane and is therefore perpendicular to the normal. Thus, R minus A dot N is equals to 0. We can then rewrite this as R dot N equals to, minus A dot N equals to 0, because the given point is just there, it's not going to run away. So we can write it as a constant equals to C, where C is the constant. Okay, so now you may wonder, what exactly is C? So visually, we actually notice that when we shift this normal to this position, to the position where you have where you are directly perpendicular to the origin, we notice that the normal is actually collinear with the perpendicular distance to the normal. So actually, this C, right, is like a dot product that represents this length over here, but with a multiple of the magnitude of vector A. Okay, so this C is basically related, if that sounded confusing, this C is basically related to the perpendicular distance between the plane and the origin. Alright, and this is explained in this 1b, point 1b. From r dot n equals to a dot n, we can see that we can replace the n with its unit vector, and this would give us r dot n equals to d. Visually, r is a position on the plane, right? This is r, this is the actual vector r. Normal vector points away from the origin. And if we have an n hat in this direction, our r dot n hat actually just tells us the perpendicular direction d, which is the perpendicular distance of the plane away from the origin. This is super important because later on you will need this to find the distance of two parallel planes. Keep that in mind. Next, we have Cartesian form. So once we have this equation here, r dot n, we can actually write it as we just expand it out. R dot n is a dot product, so we have x, y, z dot nx, ny, nz equals to c. The dot product then can be written as this form. This is a Cartesian form. Cartesian form and scalar product form can be easily converted back and forth, so this is not a big deal. But what is not super obvious is parametric form. So parametric form is not super easy to convert from Cartesian and scalar product form. Or rather, it's easy for you to convert from parametric form to scalar product form, but not necessarily the other way around. But just follow me and see how parametric form defines your plane. Suppose we have u and v non-parallel vectors on the plane with a known point A. So again, we start off with a known point. Suppose we have a plane here with a known point A. This is the origin. A is here. We can write any point on the plane as A plus lambda u plus mu v. Remember earlier, we say that if we want to define all the points on the 2D surface, we need two vectors. And this is essentially what we are doing here. We take that, let's say we have a u here and a v here. We can see that all the points along this plane can be represented as starting from point A. Starting from point A, we can represent all the points on the plane as a combination of u and v. And this is essentially what the parametric form is about. So you are using a combination of two vectors on the plane and the point on the plane to define all the points on the plane. Yeah, and if it helps, you can think of u and v as a coordinate system on the plane starting from point A. So how do we convert parametric form to the Cartesian form? We know that there's two vectors on the plane itself, right? We know there's u and v. We can represent n as equals to u cross v. U cross v will definitely give us a vector that is perpendicular to both of them. And if it's perpendicular to both of them, there's only one possible way. because they are not parallel, so there's only one possible way, which is out of the plane. Okay, so when we have two vectors, we can actually get from parametric form back to the scalar product form, because now we have an n, and we also have a point a, right? So we can write it as a r minus a dot n equals to 0, like this. Then we get back the scalar product form, and we know that scalar product form and Cartesian form are basically interchangeable. So a spin-off of the parametric form is, instead of two vectors, we have 3 points. So instead of two vectors, we have 3 points. We actually can parameterize it as as a linear combination of the 3 points, where the 3 points add up to 1. As for why they add up to 1, actually I think this is a good chance for you to practice your algebraic manipulation. Go and use the previous form here as a hint. Use the previous form here as a hint, and consider the u and v as maybe b minus a and c minus a. Try and show why kappa plus lambda plus mu give you 1. Okay, basically these are the 3 ways to represent the 3 form. Oh, and in this process, when you try and show that they are equals to 1, you realize that using the 3 point, actually you are using the same, you will be able to convert to the other parametric form quite easily. Okay, next we have relation between a line and a plane. Next is basically the relation between the plane and other objects. So a relation between a line and a plane, right, we can see that I wrote down the equation respectively here. When we have this, there are 2 possible ways that a line can be related to a plane. No, sorry, 3 possible ways. One is that it's parallel and on the plane. If it's parallel on the plane, right, m tells us the direction of the line, n tells us the normal to the plane. If they're parallel, then they must be perpendicular. If they're perpendicular, then the dot product is 0. Okay? And next is a dot n equals to c. What does this mean? A is a point on the line, but if it fulfills the criteria in the plane, we know that rp dot n equals to c. We know that any point along the plane, when we substitute the point into r, it will fulfill this equation. So if the line is on the plane, then the point on the line A, when we substitute it into this equation, should also satisfy the equation. So if it's parallel and on the plane, this equation will hold true. If it's parallel and not on the plane, then the condition for the direction of the line and the normal still hold true. But since the line is not on the plane, a dot normal won't fulfill this equation. Okay? Finally, if it's not parallel, the line will intersect with the plane, and this point can be found by substituting the line equation into the plane equation to find the common point, which is shown given this. Again, there's some unknowns. Actually, the main unknown is this lambda. The main unknown will be this lambda here. And you can find the lambda by calculating this. It's simply a dot product divided by a dot product. This can then be substituted back into the line equation, because we know line equals to lambda m plus a, where lambda can be any number and L represents all points on the line. So if now we know what lambda is, we can substitute lambda back to give us the point L. Okay, so this will give us the point of intersection. In the case of line being not parallel to the plane, the angle between the line and normal can be given by cosine equals to this, as represented in this graph over here. Okay, this direction L is basically the direction of M also, like this direction. This direction L is basically the direction of the line vector, and we can see that cosine theta, if you think this equation looks familiar, this is basically dot product. Okay, again, this is why it's so important. And therefore, because the angle between the normal and the line is equals to this theta, the angle between the line and the plane, this angle here, will be 90 minus theta. Okay. Then we have the relationship between two planes. There are only two possible ways of two planes to interact with each other. One is them being parallel. If they're parallel, then the n is the same. If they are non-parallel, n is normal. Yeah, n is the normal. It tells us basically where the plane is facing. If it's not parallel, then the line of intersection will point in the direction perpendicular to both normals. Why is it perpendicular to both normals? Think about it for a moment as I write this. The reason why the line of intersection of the two planes is not perpendicular to both normal is because the line of intersection must lie on the plane. And we know that the normal is perpendicular to the plane. So if the line is on both planes, the line must be perpendicular to both normals. And the only way we can get that would be just to use a cross product. Important, right? Cross product. So cross product, this tells us the direction of the line. Okay, so in the case of non-parallel plane, we can find the angle of intersection considering the two planes here. We can see that the angle of intersection between are actually the same as the angle between the two normal vectors here is actually the same as the angle here. If you're not sure, just add in all the 90 degrees and try and calculate. It's the same. Okay, so this angle here can also be calculated using the dot product. So this is why we say that dot product and cross product is very important, because they are applied in everywhere. So when we have a plane, we can also consider the distance of the plane from other objects. So if it's a plane and a line, one thing to note is that if the line is not parallel, if it's not parallel to the plane, you eventually cut it somewhere. You eventually have a point of intersection. So if there's a point of intersection, we can use this thing here. We can use this section. Refer to this part to find out how to find the intersection. But if they are parallel, right? If they are parallel, then we need to know the direction vector of any point on the line from any point on the plane. Any point on the line is quite easy to find because usually we have the lambda m plus a, right? A is a point on the line. For any point on the plane, it may not be so straightforward. This one you might need to guess. Okay, you might need to guess. But if it's confusing, there's always the option, because we know r dot n equals to a dot n, where a is a vector. A is a point on the plane. Okay, so a is a point on the plane. You can use this to try and guess what point it is. Okay, so once we know a point on the plane and a point on the line, we can use the scalar product with the normal to find the distance, because we see that we have a plane here. This is the normal. We know there is a line. Let's say a line that passed through like this with a distance above here. If we know a point here and a point here, let's say, and we can extend this out like this. Let's say this is 90 degrees. It has to be 90 degrees because it's the line of projection. Because it's the scalar product. Like, we are following the plane. We are following a plane. That's why we will be getting a 90 degree here. Once we find this vector, we can then do a scalar product with respect to the normal of the plane. Okay, so just now I think I didn't explain why this is 90 degree, but basically the normal of the plane would point upwards, right? So we switch to this plane, we see that we have this is the plane, this is the line, and the normal will point this way. The normal will point this way no matter what. and the normal is 90 degree. This is the point on the plane. So this is AP. This is the point on the line, AL. So to find this distance is not normal. The normal points in this direction, but it's not necessarily this entire distance. So a normal this may be more accurate. So we want to find what is this entire distance. We use the scalar product. Okay? We use the scalar product to find between AP, AL, scalar product with n hat. And this gives us the perpendicular distance between a parallel line and the plane. Alright. If the line is not parallel to the plane, it will eventually intersect and the shortest distance is 0. Okay? In the case of planes, the planes can be, in the case where the planes are parallel, the shortest distance is the perpendicular distance from one point on the plane to the other. This can be found if we write it in the scalar product form. Recall, when we talk about this, right, we see that when we write it in the scalar product form, we can actually see that the d is the distance of the plane from the origin. So if they're parallel, that means they'll look like this. On the origin may be here, then these are the two planes, side view of the two planes. We know that this is d for the first plane, this is d for the second plane, d1, d2. Then the distance between the two planes is just d1 plus d2, right? So it's quite straightforward. However, if the planes are not parallel, then of course this method won't work. But we don't have to worry about that, because if they're not parallel, they must intersect somewhere, and the shortest distance will be equals to 0. Okay? And with that, we should have covered all of the important concepts for vectors part 2. And I hope this was helpful for you. Let me know if there's anything that you find not clear. And happy studying!